Welcome back to Pi, and in today's video, I'm going to dive deeper into derivatives. So this is derivatives day 1, part 1. So let's go straight into it. All right, so let's have a recap. So in my last video, which is Intro to Derivatives, we talked about what derivatives are and their applications, and to basically just go quickly over it, derivatives can be used to calculate the slope of the tangent line or the instantaneous rate of change. And so if you don't know what those two things are, please just go and check my previous video. All right, so moving on. So notation. Notation is how we write something in math. So notation, basically what we're saying is how we can show we want to take the derivative of something, or how a question may ask us to take the derivative of something. So there's two types of ways of representing a derivative. There's the Leibniz notation and the Lagrange notation, and I'm sorry if I misspelled both of them. So looking at the first one, the Leibniz notation, you can write it as dy over dx, or you can just write it as d over dx multiplied by f of x, because they're both the same thing. Y is equal to f of x. It's the same meaning. For the Lagrange notation, we have y, and we have something that looks kind of like an apostrophe, but I'll talk later about that. It's not an apostrophe, but it's similar to it. So we have y and then something similar to an apostrophe, or you can write it as f, again, something similar to an apostrophe x. All right. So let me show you what I mean. So in derivatives, I have the right one. For example, if I want to show that this is the derivative of a function, I can use the Lagrange notation and write y, this thing, equals, for example, 3x plus 2. All right. So this thing is actually not an apostrophe. It looks similar to it. It's called a prime. All right. So it's called prime. Prime. So the way we say it is y prime is equal to 3x plus 2. Or if I was to use the f prime of x example, it would be f prime of x is equal to 3x plus 2, for example. So what this is saying is that this function right here is the derivative of the original function, which in this case is just an example, so I don't know, but this is just an example. So this is how we can represent derivatives in the Lagrange notation. So going back, the Leibniz notation, it's different in that it doesn't use the prime symbol. It just says, again, dy over dx, is equal to 3x plus 2. It's the exact same meaning. You can use either one. They mean the exact same thing. Or again, you can say d of dx, and then there's like a function here is equal to 3x plus 2. All right. So you can use both of these, and this means that the derivative of whatever function is equal to 3x plus 2. Now, if you have an original function and you want to show that you want to take the derivative of it, the way you do that, let's say that, for example, you had x cubed plus 2x, and you wanted to find the derivative. The way you would do that is you would write, for example, this function, you would write f prime of x, if this is f of x, let's just say that f prime of x is equal to, and then you would obviously use the rules I'm about to explain to find the derivative. So one last thing I want to mention about the notation is that out of both of these, I prefer the Leibniz notation, actually. I prefer the Leibniz notation for a number of reasons, which I will get into later on. The Lagrange notation is also helpful and it's very easy to remember. However, I prefer the Leibniz notation. I'll talk more about that as we move later on. But for now, feel free to use whichever method you want. It's completely up to you. Again, they both mean the same thing. A lot of people also like, again, the Lagrange method because they find it easier to use, and they find it less intimidating. So please feel free to use whatever you want. All right, so let me move on now. So let us actually get into the subject of finding derivatives. So there's actually two ways to find the derivative of a function. There's the first way using limits, and there's the second way using differentiation rules. So in these set of videos, we are actually going to be focusing on using differentiation rules. Why? Because they are more efficient and easier, and they're actually meant to find derivatives, hence the name differentiation. And differentiation, by the way, is the process of finding a derivative. Using limits is something I'll make a very brief video about. It's not my main concern for this topic, but I will mention it. And it's also a helpful tool that can find derivatives, but it actually takes longer, and it might be a bit more complicated. The differentiation rules, on the other hand, very quick, very smooth. You don't need a calculator. And they're actually meant to find derivatives very, very easily. Limits, again, I'll touch up on it, but these series of videos will all be about the various differentiation rules to find derivatives. All right, so let's move on. All right, so differentiation rules, what are they? Differentiation rules are a set of rules we follow when we differentiate. So it's very straightforward. Basically, when we try to find the derivative, there's a certain set of rules we have to follow to make sure that we have found the right derivative for that function. So now I'm going to be showing you the core differentiation rules that we use. And in later videos, I'll be building up on these rules and showing you the more advanced rules. But for this video, it's just the basic core rules, and they're very basic, very straightforward. So let's just go right into it. All right, so the derivative of a constant function. This is the first rule when we try to find the derivative of a constant function. So again, you can see constant function is represented by k. So a constant function can be like, for example, y is equal to 3, or y is equal to pi, because pi again represents 3.14. So a constant function is just a number. It doesn't have to be a whole number, just a number. So when we find a derivative, again, look how they use the notation. They use d over dx, which means we're trying to find the derivative of a constant k is equal to 0. So that's a very straightforward rule. Whenever you try to find the derivative of just a constant number all by itself, such as in these two examples that I've put up, it will always be equal to 0, where k is equal to all real numbers. That's what this says right here, where k is equal to all real numbers. And note, k does not have to be strictly numbers. It can be symbols like I just showed you. So symbols that represent numbers, right? So that's the first rule, and we're going to talk more about that. So this is the proof. Again, it uses limits, and to people who know limits, this will make sense. But essentially, it proves that at the end, the derivative of k is equal to 0. And you can check out my website for more explanations on that. I'm not here to do the proof. You most likely do not need the proof for high school level. You probably need it later on. And again, if you want to get the full understanding, the full proof, please check out my website. But I'm not going to be using limits because I'm going to assume we still haven't learned limits. So instead, I'm going to try and prove it graphically. So you can think about it as well. So let's say we have, let's say this is 0, this is 0, this is 0, right? And let's say this point here is 3, okay? Let's say it's 3. So f of x, let's say we have a function f of x is equal to 3. What that means is that the entire function will just be a straight line with a function value of 3, all right? So if you can recall, the derivative is finding the slope of the tangent line, all right? And even when we look at this graph, it's never changing, okay? There is no rate of change. A slope is a rate of change. There is no rate of change because it's a flat line. So in any, like, for example, on this point, let's say this is 1. I know this is not the scale, but it's just for the sake of example. Let's say this is x is equal to 2. So obviously x-axis, this is your y-axis. Let's say we have a point here and here. In both cases, the function value or the y value will always be 3. It is not changing. And therefore, there is no rate of change. And 0 represents 0 rate of change. This function will always be 3. The function value will always be 3 for whatever x value you have. Therefore, your slope will always be 0. And the slope of the tangent line will also be 0. That is why your derivative for a constant number will always be 0. So the derivative of this function of f of x is equal to 3 is 0. So that's the first rule for differentiation. Now here's two examples, and this is how I'm going to represent those examples. So first, for a, find the derivative of f of x is equal to 9. Again, 9 is a constant number. That means like in our past graph that I just showed you, it will be a straight line at 9. The function value for whatever x value will always be 9. So now let me show that I want to take the derivative. I'm going to write the proper notation. So f prime, which is again the thing that kind of looks like an apostrophe, of x is equal to 0. That's it. You solved that problem. It's very straightforward. That is all you need. You're done. All right. Yeah, that's it. And now let's move on to b. F of x is equal to pi. Now, you might first initially think, well, oh, pi is not a number. But if you think again, actually it is. Pi is just a symbol, but it stands for a number. It stands for 3.1428 and so on, so on, so on. So it's actually also a number. So if we had a graph similar to this, it will also be a straight line just going through and never changing. The slope or the rate of change will always be 0. So again, I can write this as well. And let's say this time I want to use another form of notation. So I can say dy of dx is equal to 0. And these two both mean the same thing. There's just two different types of notations. Both of them are fine. Both of them mean the exact same thing. And this one is also 0. And that's it. You solved this problem. So the first rule, very straightforward. Very easy. Now let's go into the second rule. This is a very important rule, so please pay attention for this one. The derivative of a power function. So again, d over dx of x to the power of n is equal to nx to the power of n minus 1. This might be intimidating at first, but it's really not. All we're saying is that when we have a variable as a base and it is to the power of a number, that number will come down, and whatever number was here, you subtract 1 from it, and that is the new derivative. And I'll explain this more obviously, but let me just get your attention for a second. You need to take caution. There's a difference between a power function and an exponential function, and I will talk about that right now. A power function is when you have a variable such as x, v, z as a base, and you have a number as an exponent, right? So base, exponent. I don't know if that's exponent. An exponential function is the opposite. It's when you have a number in your base and you have a variable in your exponent. So that's the difference. So for example, 2x, right? 2x is an exponential function, so you need to be careful. You cannot apply this rule to something like this. This is not allowed. An example of a power function, for example, can be this, x squared. That is a power function. This is allowed. This rule applies to this. So the thing with differentiation rules is that you need to apply the right rules to the right condition, because if you don't do that, you will get a wrong answer. And that's pretty much the core of what I'm trying to teach you guys here. There's a set of rules. They're very straightforward, and you'll get better at them as time advances. But you just need to make sure to follow the rules. All right. So again, this is for power functions. Please pay attention to that, not exponential functions. If you see something like a number and it has a variable as an exponent, that cannot work. You cannot use this rule. Now let me dive deeper into how this rule works. So for example, find the derivative for a, x cubed. All right, so let me say f of x is equal to x cubed. All right, now let me show that I'm taking the derivative of that. All right, so f prime of x, and then remember the rule, right? Let's go back to the rule. Oops, that's going forward. So you bring down the exponent, it comes down, and then you subtract that number by 1, all right? So there's a 3 here. This 3 is going to come down right in front of the x, so 3x, and then we do 3 minus 1. Let's make a new line. F prime of x is equal to 3x. 3 minus 1 is 2, so 3x squared. 3x squared is the derivative of x cubed. And that's it. That's the answer. You are done. All right. Now let's move on to something a little bit trickier. The square root of x. Let's find the derivative of that. Right. Now, if you know or you may not know, this is kind of part of your exponents unit that you might have taken. To represent, you can represent a square root using exponents, and the way you do it is like this, right? So the square root of x turns out to be x to the power of 1/2. And the reason we do it like that is because it's always going to be a function, a fraction for square roots, and your top number is going to be the exponent of the variable inside. So in this case, x is all by itself, so we assume that it's x to the power of 1. And the number on the bottom, the denominator, is going to be your index. The index is the number that goes here. Now, for 2, we don't need to write 2 because it's almost like an international standard. If you just put the square root sign, you're automatically meaning 2, all right? But for example, we could also have for this like the square root of 3 and x squared. I'm not sure if that's the best, but it will be represented as x 2 over 3, right? Because that's the exponent that x is that's the exponent for x, and then the index goes on the bottom. So always for square root, you can set it up as a power function, and the way you do that is the exponent that x is to the power of becomes the numerator, and your index, for which determines the value of the square root, is your denominator, right? So this is how we set it up. So now let's find the derivative. Again, f prime of x means I'm taking the derivative. And again, this number comes down, so 1/2 comes down, x, and then we write 1/2 minus 1, all right? Now, as you're aware, we don't need to, I don't think this is too complicated. 1/2 minus 1 is -1/2. And that's it, you're done. That's the answer. All right, so that's power functions. That's the rule for power functions. Now let's move on. I have a short quiz for you. If you guys want, pause the video here, try to solve these yourself, and I'm going to be shortly giving out the answers. All right, so now let's find the answers for these questions. So let's start off with number A. Let's start off with question A. All right, we want to find the derivative of f of x is equal to 3/4. F of x. All right, so this relates to our first rule, if you can remember. The derivative of a constant number is always 0, all right? So this is a constant number. Even though it's to the power of something, 3 to the power of 4 still just turns out to be a number, a constant number, all right? So I'm just going to show that very quickly. F prime of x means the derivative of this function is 0, and that's the answer for A. Let's go on to B. All right, B, g of x is equal to 1 over x to the power of 3. G of x. All right, so this is the problem, and now let's solve it. So let's put the prime sign, g prime of x. All right. Actually, sorry, let's not do that. Just remember something. All right, so again, going back to your exponents rules, if you see something like 1 over x to the power of something, all that means is just x that can be represented as x to the power of -3. Oops, -3. All right, so it means the exact same thing. These two mean the same thing. If you're seeing a pattern for the power functions, we always want to turn them into this form, so that they're very easy to solve, because we can't really find the derivative of a power function when it's in the form like this. We can't really do that. It becomes very hard, right? So we always try to convert it into a form where we have a clear power function and we have a clear exponent. All right, so now this becomes very easy. G prime of x, please don't forget this sign, very important. G prime of x. We bring the -3 down, so the -3 comes down, all right? And then we do, I'm just going to do it here on the side. -3 minus 1 is -4. So that's another thing you need to pay attention to. If you have a negative exponent for the power function, it's not going to be necessarily a subtraction. In this case, they're both negative, so it actually adds up in a sense to -4. Please pay attention. A lot of people in my class had this mistake where they do, oh, they'd rush it, they write -3 minus 1, oh, -2 or +2. Please remember, if it's a negative and you subtract 1, you're actually increasing the value of the negative of the integer, so it's now -4. Technically you're decreasing the value of the integer, but that means that it's now a larger negative number. So now it's like -4. So that's a very important point to pay attention to. Now I'm going to clear the page and go back. All right, C, y is equal to the, all right, to the 4th root of x cubed. Let's just write that down. Y is equal to the x cubed, the 4th root of x cubed. All right. Okay, again, if you go back to what I just talked about, we can represent this first the same way as we did previously. So again, if we have any square roots or cube or whatever, if we have a root problem, the way you can actually turn this into a power function is this becomes the numerator, and this becomes the denominator of the exponent that's going to be the power for the power function. So 3 is here, so 3 becomes the numerator and 4 becomes the denominator. So now it's x to the power of 3/4. And now again, very simple from here, we can find the derivative y prime. This is one of the methods, if you recall, for finding derivatives, equals to the 3/4 comes down beside the x. And this is the x. And now we do, I'm just going to show my work. It's very important to show your work and to take your time. -1. Again, this should be very straightforward. It's 1/4. If you don't know how to do it, or if the fraction is too complicated for you, just remember how to subtract fractions. So just 1 would turn into, has to have a common denominator. That would be 4. So we can do that. And oh, and I made a mistake. See, that's why you show your work. So 3 minus 4 is actually -1. Even I got that wrong. Okay, so it's actually -1 divided by 4. So it's to the power of -1/4. And yeah, that's your answer. So I guess this kind of shows that even I can make mistakes if you don't follow the rules or if you don't pay attention. So yeah, to really watch out for that -1 and take your time. It's fine. All right, now let's go on to the last question. D is equal to r of x is equal to pi to the all squared, pi squared. All right, so let's write this down. D of x, sorry, r of x, not d of x. R of x is equal to pi squared. All right, now again, let me show that I'm taking the derivative of this. There we go, that's the derivative. And remember, this might be a trick question. This is actually a constant. It's just a constant number. It's kind of like saying 3.14 all squared. And to that, the answer is 0. The derivative of a constant number is 0. And that's the answer. And there we go. We have now solved all 4 answers, all 4 questions. So let's move on from here. All right. So for this one, this is the rule for finding the derivative of a constant multiple of a function. A constant multiple is a number that is usually right beside the variable. So for example, 5x, 5 is a constant multiple. This actually means 5 times x, but we don't need to show that. We can just stick them together and people will understand that this means 5 times x, or we can just say 5x. For example, 12x squared. These are all just random examples, but they all mean the same thing. This is a constant multiple, right? So the rule states the derivative of a constant multiple of a function. Let's find out the rule. So when we're taking the derivative of whatever function we have, the constant is not affected. So if you recall earlier, I just mentioned that the derivative of a constant all by itself is 0. However, if I was to try to find the derivative of 5x, what this rule is saying is that to leave the constant multiple out of this, right? So if we have a constant multiple, not just a constant number, so a number that's actually attached to a variable, like in this situation, what we do is we actually do not care about this constant multiple. We leave it out. We still multiply it, However, we only focus on the variable. So we only focus on this. That's what this rule is saying. When we take the derivative, we leave the constant out of it. We only focus on the function, the variable. So the constant multiple of the function is left out. We don't do anything to it. It's not 0. It just remains. It's going to be multiplied with the derivative of the rest of the function. So let me show you an example. So for example, find the derivative for 5x squared. All right. So again, when I'm trying to find the derivative for both of these, let me just write this. The derivative for 5x squared, we actually have to break it up, all right? So this actually turns into 5. We leave 5 alone. And then we take the derivative of x squared, like as such, all right? And now again, we can, for this one, we just learned about this. It's a power function. The 5 stays here. We bring down the 2, and 2 minus 1 is 1, which is just 2x. And now we can multiply it again. 5 times 2 is 10. So 10x is the derivative for 5x squared. That is the answer, all right? So that is how, that is an example of using the, to find the derivative of a constant multiple of a function. And now for this one, take your time to do it by yourself. So if you want, you can pause the video. All right, and now I'm going to be showing you the answer. So d over dx of 2x to the power of 6, right, equals, again, we leave the constant multiple out of it. It is not involved in the differentiation process. We only focus on this, on the power function. 2 stays like this. We bring 6 down, and then remember 6 minus 1 is 5, so 6x to the power of 5. Now we're just going to multiply these, very simple. 2 times 6 is 12, so 12x to the power of 5 is the derivative of 2x to the power of 6. And that's it, you're done. Right? Oh, I'm supposed to do the answers on this page, but we had room on this page, so it's fine. Let me just write them very quickly. Answers for A, 10x. For B, 12x to the power of 5. 12x to the power of 5. All right, now let's continue. All right, so this is our last rule for today. I know I've given you guys quite a lot of rules to remember, but again, you can rewatch the video, you can pause it, you can take notes on your notebook. And again, please check out my website. I have full notes, full explanations for all of these. So I'll put a link to the description. I'll put a link in the description below for that as well. All right, so now let me just go back and focus on my last rule for today. So the derivative of a sum or difference of functions. So what if you don't have one function? What if you're adding or subtracting two different functions? Well, this is the differentiation rule for that. It's actually very straightforward, very simple. So when you're taking the derivative, if you want to find the derivative for two functions that are either being added or subtracted, all you do is you kind of, it's similar to expanding the bracket. So for example, if you have something like this, right, what you do is you actually expand this. You multiply the 2 with everything, so it becomes 2 times x plus 2 times 2. And this same concept applies to this rule. So all we do is we literally just bring this and we take the derivative of each function, and we keep the subtraction or addition sign, and as you can see, we take the derivative of this and add it or subtract it to the derivative of this. So very straightforward. And yeah, that's all we do. And this is just a blank page. All right, and this is, so let's do this example together. All right, so we have multiple functions here. We have one function, but it's comprised of multiple parts, and there's addition and subtraction between them. So this rule actually still applies. So that's another thing I wanted to touch up on. This rule does not necessarily have to apply for only two functions being added or subtracted. It also applies to one function that has multiple additions or subtractions in the function. So let us do this one. All right, so this is the function. Let us find the answer. Again, very straightforward. Let me represent this by saying I am finding the derivative. F prime of x is equal to. All right, first off, we are going to find d over dx 2x 5. So again, we expand it. We take the derivative of all the different components. 4 over 3. We break it down. Minus d over dx of 7x minus, don't know if I have any more room here, d over dx of, ooh, that's not writing, right, but there's a 5 down here. There's a 5. All right, so now let's elaborate further. So now we just remember our rules, and this is very straightforward. For the first one, remember, this is a constant multiple right here. This is a constant multiple, so we ignore it. We just leave it outside, and we take the derivative of x to the power of 5. Now, if you remember, this is a power function. The 5 comes down, and we do, for the exponent part, we do 5 minus 1, which is 4. So it becomes x to the power of 4. Now, again, leave the plus sign. There's a plus sign here. It stays, all right? And then we have the derivative of 4/3 times x to the power of 3. Again, this is a constant multiple. It's attached to the variable. We leave it alone. And then we take the derivative of this power function. This one's straightforward. We bring 3 down, and 3 minus 1 is 2, so 3x squared. Minus subtraction sign stays as well. Another constant multiple. We leave the 7 alone. However, x is only to the power of 1. So if we have this condition, 1 minus 1 is 0. X to the power of 0 is just 1. Not 0, it's 1. Please pay attention to that. And for the last one, very straightforward. It's just a 5. So this is not a constant multiple because there's no variable attached. It's just a number. The derivative of a number is 0. And again, subtraction sign stays. Right? So now let's elaborate more on that. Let's clean everything up. All right, so for the first one, 2 times 5, x to the 4, that's just 10x to the power of 4, plus, all right, now 4 over thirds times 3x squared. Remember, since this is multiplication, we do not need common denominators for these fractions. We can just directly multiply the 3 with the 4. So 4 times 3 is 12, all over 3, and the x squared, okay, and then 7 times 1 is just 7, very straightforward, minus 0. And now let's clean that up even more because it can be made neater, right? So this stays 10x to the power of 4. 12 divided by 3 is 4. So it's actually a whole number, so that's very nice. 4x squared minus 7. And the 0, well, it's 0. We don't need to write it, so we can just write this. And this is the derivative. In other words, this is the slope of the tangent line for the general derivative for the slope of the tangent line of this function, right? So this is the answer. Again, very straightforward, very simple, all right? And that's it for today's video. I know I've given you guys a lot, but thank you so much for tuning in. And again, please feel free, check out my website in the description. It's very good. It comes in, I have full notes for everything. I have extra practice problems for you guys, and I also have the solutions to those practice problems with full work shown. So in some textbooks or some websites, there is answer sections, but when you guys go to them, they just give you the answers and you don't even know how they did it. So what's the point of that? I have practice problems with full work shown, full solutions, so you guys know the steps and how I got the answer. Again, thanks so much for tuning in, and stay tuned for more videos.